from x equals sine y, can I find dx dy? Certainly. Dx dy is cosine y. Now, look at, we didn't want dx dy, we wanted dy dx. But since we're on a one-to-one strip here where the inverse function does exist, notice that the relationship between dx dy and dy dx is that they are reciprocals of one another. That was exactly one of the nice properties of this notation that we've talked about on several occasions before. In other words, dy dx is 1 over cosine y. By the way, I like this better than saying things like the reciprocal of cosine is secant. I think when you print a book, people like to use secant instead of 1 over the cosine, simply because you can get everything on one line and don't have to write fractions this way. But that is not our major concern here. What I do want you to see is, given that y equals inverse sine of x, can I find dy dx? The answer is yes. And by the way, notice that this is perfectly well defined. Namely, for a given value of y, cosine y, you see, is single valued. For a given number, it has only one cosine. You see, I don't need single valuedness to get this result. The place I have to be careful about inverse functions existing is that since there are many different x values that correspond to the same y value, if I don't specify, you see, if I have a multi-valued function, if I don't specify what branch I'm on, the trouble will not come in when I'm looking for dy dx at a given value of y. It's that 99 times out of 100, when you're looking for dy dx, y is given as a function of x. In other words, you want to be able to convert this in an unambiguous way into a function of x. See, that's the question that comes up. There is nothing wrong with this answer. In other words, I can write down that dy dx is 1 over cosine y, but somebody can say to me, I'd like the answer in terms of x. By the way, how can I get this answer in terms of x? That's an interesting question sometimes. You see, recall that y equals inverse sine of x says the same as what? X equals sine y. Now, what identity do I know? I know that sine squared plus cosine squared is 1. See, x squared is sine squared y. Okay? Now, what do I know? I know that cosine squared y is 1 minus sine squared y. So cosine y is plus or minus the square root of 1 minus sine squared y. That's plus or minus the square root of 1 minus x squared. Notice, by the way, in this notation, that y wasn't any old number. Y had to be in what range? Y had to be between minus pi over 2 and pi over 2. And as long as that's the case, notice that in that range the cosine is positive. That makes the negative sign redundant. See, and by the way, that negative sign would not be redundant if we hadn't restricted our range to making the curve single valued and 1-to-1. You see, it's the restriction that y has to be between minus pi over 2 and pi over 2 that makes this the positive square root. In other words, then, what we see is what? That therefore, dy dx is equal to 1 over cosine y. That's 1 over the square root of 1 minus x squared. And that's a rather interesting result. It's a rather straightforward result. I would like to make a few comments about this thing. And one of them is what I want to summarize with later, too. Suppose you were given a problem of saying, I would like to trace a curve, or plot a curve, and all I know about that curve is that its derivative at any point is 1 over the square root of 1 minus the square of its x-coordinate. Do you have to know any trigonometry? Do you have to know any trigonometry to understand that problem? In other words, notice that this expression in no way utilizes trigonometry. Yet to solve this problem, it appears from what we've shown is that what? That given that the slope is this, the curve itself turns out to be y equals sine inverse x. And that is an inverse trigonometric function. And so here's a very important reason as to why the trigonometric functions are that important.